Hello everyone and welcome to today's lecture. Today we are going to deep dive into the determination of vitamins and antioxidant. And I'm Associate Professor Dr. Muhammad Razif Shahril from University of Bahasa Malaysia. Our main focus today will be looking closely at the determination of vitamins, specifically within the foods. By end of this lecture, you should be able to describe the principle behind the analysis of vitamins, compare methods used to analyze vitamins, and describe methods to analyze antioxidant. So we are going to start with a very familiar yet highly important nutrients in the human diet, the ascorbic acid, commonly known as vitamin C. Now you might be thinking, ascorbic acid is an acid, so why can't we just measure its concentration using a standard simple acid-base titration? So the answer lies in the complexity of the food matrices. We cannot measure the concentration of acid-base titration because there are simply too many other naturally occurring acids and bases in foodstuffs and other products. So this would heavily interfere with an acid-base titration, giving us widely inaccurate results. So to get around this, we normally use a particular high specific redox titration to determine its concentration. So you can see the chemical structure of vitamin C here in the screen. So the specific redox titration we use is called the indophenol method. We use a chemical called 2,6-dichloroindophenol, DCPIP, for short, and this DCPIP is fantastic for its application because it is quite specific in its ability to oxidize only the vitamin C. So it's an organic dye that possesses both acid or base and redox properties. Visually, this dye is highly reactive to environment. It is dark blue in neutral and basic solution, but it turns into distinct red in acidic solution. So on the next slide, you can see the exact redox reaction taking place here, where the vitamin C is oxidized by DCPIP in a 2-electron, 2-proton transfer. So what are the visual principles of this titration? So the DCPIP acts as a red dye that possesses oxidizing capacity. So when we titrate it against our sample, the DCPIP loses its red color as it is reduced by the ascorbic acid through that redox reaction we just looked at. So as long as there is a reduced ascorbic acid still present in our sample, the DCPIP will continue to fade. So the magic happens the moment the reduced ascorbic acid is completely depleted. At that exact moment, the DCPIP will display its original red color. Therefore, the content of the reduced ascorbic acid can be accurately calculated according to the amount of DCPIP consumed during the titration. So before we test our food samples, we have to do a standardization run. So why do we do this? So there are two reasons. First one is to find the approximate volume of DCPIP needed to actually reach the endpoint. And the second reason is so you can become more familiar with the specific color change at the endpoint. So the endpoint is reached at the appearance of a beige color. So if the color fades, it means ascorbic acid is probably being gradually released from something it has absorbed on. So the golden rule here is that if the solution holds its beige color for 30 seconds, you have officially reached the endpoint. Just be consistent throughout the experiment. So we're moving on to the analysis of liquid samples. There are a few prep steps for this. So solid samples must first be made into aqueous solution. So you must ensure the solution is completely free of other oxidants that will also oxidize the DCPIP and ruin your results. So also, if the expected ascorbic acid concentration is not in the effective range of our setup, we will have to concentrate or dilute the sample appropriately. A major consideration is samples should be prepared immediately before the titration. So if you have to must prepare them several hours earlier, you can you can minimize unwanted oxidation by adding a small amount of oxalic acid, typically around 1 gram per 100 ml of your sample solution. So now, what happens if you are testing colored sample like a dark fruit juice? Identification of the endpoint in this titration is significantly affected by the coloration of the sample solution. So you will need to carry out a rough titration first just to become familiar with any distinct color change which occurs at the endpoint. Sometimes it isn't beige, it may just be a slight darkening of the color. This rough run helps to establish an appropriate volume required. So ultimately, keep in mind that this titration method is generally not suitable for deeply colored juices. Here on the screen, you can see a standard setup with the burette containing the DCPIP solution dispensing into the conical flask holding our vitamin C sample solution. So why is this analysis so important? It has some serious legal and consumer implication. Example, back in March 2007, the pharmaceutical giant GlaxoSmithKline or GSK has taken to court in New Zealand and Australia, facing millions in fines because high school science student tested Ribena drinks using this exact method and found almost no vitamin C, proving that the company's advertising was completely misleading. So the application of this titration are vast. We can use it to find vitamin C content of different fruits, vegetables, and juices, test different brands of vitamin tablets, and even track how vitamin C content degrades before and after the subjection to cooking um, um, condition or different stages of fruit ripeness. So let's look at the calculations. First, we prep our solution and our standard. We must calculate the interphenol dye factor denoted as F. So the F is equals the weight of ascorbic acid used in milligram, usually 2.0 milligram, divided by the volume of indophenol dye used in the titration. So to find the ascorbic acid composition in the orange juice in milligrams per 100 ml, we take our F value, multiply it with the volume of the dye used for the sample minus the volume of dye used for the blank, and multiply that with 100 over the sample volume. If we were testing orange peel, we use slightly different formula that factors in the total volume of the prepared sample over the weight in grams. So let's do a quick exercise. If we use a um, if you use 2 milligram of ascorbic acid and it takes an average of 7.7 ml of dye to reach the endpoint. Our F value is 2 divided by 7.7, which is equal to 0.26 milligram per mil. You will then plug that 0.26 F value into the orange juice or orange peel volume formulas alongside the specific titration volumes you recorded from your essay to find the final milligram of vitamin C. So So the determination of vitamin content can be used for biological liquids, um, plant or animal tissues. So the general principles are still the same, but the extraction method differs depending on the matter being analyzed. So the real problem is the extraction procedures. The current change in legislation that permits vitamin supplement food substances necessities constant analytical control and underlines the importance of the methods to determining this vitamin C. So let's first focus on the liposoluble or fat-soluble vitamins because these vitamins are trapped in fat matrices. So our extraction requires a very aggressive chemical approach. So here's the global extraction technique. First, you weigh a proper amount of food substance and transfer it to 150 ml round flask, and then you add 10 ml of strong base. There's 33% of potassium hydroxide and 40 ml of ethanol. You boil this mixture at reflux for 30 minutes to achieve saponification, breaking down those fats. And next, you cool it very rapidly, neutralize it by adding 17 ml of 25% hydrochloric acid, and cool it again. We then add 15 ml of petroleum ether and shake vigorously for 3 minutes to pull the vitamins into the organic phase and wait for complete separation of the two phases. Remove and filter the organic phase through and hydrosodium phases to dry it, and finally evaporate it to dryness in a vacuum of at a gentle 25 degrees Celsius and re-dissolve the residue with a known volume of hexane to prepare it for HPLC analysis. So let's look at the specific nuances first for extracting vitamin A. So we start by weighing 5 to 10 grams of crushed food substance into a 1 liter round flask, and then we add 20 ml of 50% sodium hydroxide solution and warm it in a water bath. We also add 100 ml of diethyl alcohol and 2 ml of hydroquinone solution where we maintain that water bath at a hot 90 degrees Celsius exactly 30 minutes. And after decanting it into a vial and adding a water, we use ethylic ether and petroleum ether to shake and extract the samples. We wash the ether phase 3 times with water, then filter, evaporate, and concentrate it until we have just 1 ml left. So there are two massive concentration here. First, every single one of these steps must be conducted strictly away from light to prevent the vitamin A from degrading. Second, if the product you're testing is non-fatty, saponification with an sodium hydroxide is entirely unnecessary. So what about vitamin D2 and D3? Okay, so this is again the extraction method for vitamins D, and where we take around 5 to 10 grams of our sample, but this time we add proponyl prio, priopanol, um, absolute ethanol, and a 50% potash solution. So we extract these three separate times using 50 ml of petroleum ether. After washing the ether, extract 3 times with water. We filter, evaporate, and concentrate it down to just 1 ml. Just like vitamin A, saponification with the alcoholic potash mixture is not necessary if your sample doesn't contain fats. So for vitamin E extraction, brings in a unique challenge because it's so sensitive to oxidation. So we have to weigh 5 to 10 grams of crushed foods, but before we heat it with a strong base, we have to add 100 ml of ascorbic acid methanol solution to avoid oxidation. So this ascorbic acid acts as sacrificial antioxidant to protect the vitamin E. So we keep this in a boiling water for 15 to 20 minutes, and then we add our strong base, 15 ml of 70% of calcium hydroxide solution. We return it to the water bath for 40 minutes. After decanting and washing, we extract it with ethylic ether and then filter, evaporate, and concentrate it to 1 ml. And again, if there is no fat, there is no need to saponify. While we have covered the main protocols, remember there are other specific extraction techniques detailed in the official analysis methods proposed by AOAC. So once we have our 1 meal concentrated extract, numerous determination techniques can be proposed. We can use fluorometry and colorimetry, liquid phase chromatography with ultraviolet or fluorometric detection. We can use gas phase chromatography, which is particularly good for vitamin E, or even microbiological determination. So for vitamin A, this determination is carried out directly on the solvent of the liquid extraction. So for determining vitamin D2 and D3 and their metabolites by liquid chromatography, we use very specific conditions. So we use a C18 reverse phase column for this determination, and the solvent is a precise mixture of 55% acetonitrile and 45% water or acetic acid. And we run the flow rate at 1 ml per minute, set our detection wavelength to 265 nanometer, keep the solvent at 25 degrees Celsius and oven at 40 degrees Celsius. So we keep in mind that for some food, modern labs can determine all three of these fat-soluble vitamins, whether it's vitamin A, D, and E simultaneously. So let's shift gears completely to the hydrosoluble or water-soluble vitamins, because we aren't finding at a fat matrix. The general principle here is simply that the sample must be crushed as finely as possible, and we frequently rely on enzymatic extraction using amylolytic or proteolytic enzyme rather than harsh bases. For example, to extract the assemble of hydrosoluble vitamins, we homogenize the finely crushed sample at zero point 0.1 molar HCl and heat it at 100 degrees Celsius for 30 minutes. We then cool it, adjust the pH to 4.5, and add specific enzymes like beta amylase and takadiastase, and incubate it at 37 degrees Celsius overnight. If we are extracting ascorbic acid for vitamin for HPLC, we weigh the samples and decant it into a 50 ml flask using a zero point 0.4 metaphosphoric acid solution, and we filter it on a cellulose acetate membrane, pass it through a SAP pack C18 cartridge, eliminate the first 2 ml, and collect the next 5 ml for analysis. So now let's look at how we specifically determine vitamin B1 or thiamine. We have three main venues. First is fluorometric detection, where after applying potassium ferricyanate in the presence of potash, we determine the fluorescence using 360 to 365 nanometer primary filter and 460 to 480 nanometer secondary filter. In using the microbiological determination, we use bacteria. Depending on the chemical methods, we can use specific lactobacilli strains like Lactobacillus fermentum or Lactobacillus viridis ATCC 1207C. The statistical calculation of this activity is based on the specialized 6 points method. And the third method or The third method that we can use is using the liquid chromatography, HPLC. Just like vitamin D, we use a C18 column specifically to 25 centimeter by 4.6 mm um, um, and 5 micrometer internal diameter. And the solvent is methanol and 0.005 molar sodium acetate buffer adjusted to 4.5 pH, running at 1 mil per minute. The key difference here is the detection. We use fluorometric detection with an excitation wavelength at 366 nanometer and an emission wavelength of 435 nanometer. So let's move on into our final major part for today, which is the determination of polyphenols and antioxidants in food. First, we must define what is antioxidant. So by definition, antioxidants are compounds capable of either delaying or completely inhibiting the oxidation processes that occur under the influence of atmospheric oxygen or reactive oxygen species. Because this protective capability, they are widely used for the stabilization of various products, not just foodstuffs, but also polymeric products, petrochemicals, cosmetics, and pharmaceuticals. In human body, they are heavily involved in defense mechanism against pathologies associated with attack of free radicals. So we can look at several specific examples of antioxidant use in the industry. Some are synthetic, such as BHA, which stands for butylated hydroxyanisole, or BHT, butylated hydroxytoluene, and TBHQ, which is tertiary butyl hydroquinone. So we also have naturally occurring antioxidant like tocopherol, which is vitamin E, as well as propyl, octyl, and dodecyl galates or their mixtures. So these compounds serve as a critical function in food production to preserve the freshness and extend shelf life. You will routinely see them added to commercial products like vegetable oil, cooking fat, peanut butter, and coconut cream. So antioxidant can be broadly classified into two major categories like enzymatic and non-enzymatic. So enzymatic antioxidant include primary enzymes like superoxide dismutase, catalase, and glutathione peroxidase, and non-enzymatic antioxidants which we generally get from our diet include minerals like zinc, selenium, carotenoids with beta carotene and lycopene, and our vitamin A, C, E, and K. Another massive subgroup of non-enzymatic antioxidant is polyphenols, which further branch out into flavonoids and phenolic acids. Now, how do we actually determine antioxidant activity in the lab? So, antioxidant can essentially deactivate radicals by two major mechanisms using the HAT and SCT, and the end result is ultimately the same regardless of which mechanism that occurs, but the kinetics and the potential for side reaction differs significantly. So let's look at the first mechanism, the hydrogen atom transfer, HAT. So HAT assay measures the ability of the antioxidant to quench free radicals by hydrogen donation. So these methods generally use a synthetic free radical generator and oxidizable molecular probe and your antioxidant sample. So the great thing about HAT reaction is that they are solvent and pH independent. They are also usually quite rapidly, typically competing in just seconds to minutes. And because of this speed, we quantitate the results by monitoring the competitive reaction kinetics. The second mechanism is single electron transfer, or SET, and these assays detect the ability of the potential antioxidant to transfer just one electron to reduce any compound, which could include metals, carbonyls, and radicals. So the SCT methods involve a single redox reaction where the oxidant acts as an indicator of the reaction endpoint. Unlike HAT, SET reactions are usually quite slow and can require longer time to reach completion. Because of this, calculation for SET antioxidant capacity are based on the percent decrease in the product rather than kinetic curves. So there are many in vitro assays based on this mechanism. Assays involving HAT include ORAC, which stands for oxygen radical absorbance capacity, and TRAP, the total radical trapping antioxidant parameter. So on SCT, we have TEAC, the Trolloc equivalent antioxidant capacity, and FRAP, the ferric ion reducing antioxidant parameter. So most of the assays utilize calorimetry, relying on the fact that differences in color results is in differences in the absorption of light can be measured with the spectral photometer. For example, the DPHH and ABTCS assay use calorimetry to measure the reaction with organic radicals, while the ORAC relies on the loss of fluorescence. So let's focus specifically on the determination of total polyphenol content, or TPC. The gold standard for this caloric metric measurement is known as Pauline Kikatau assay, um, or TPC. Okay. Um, Sorry, the gold standard for this is a calorimetric measurement known as the Pauline Kikatau assay, and this assay relies on the reduction of phosphomorbidic phosphotungstic acid reaction, the Pauline reagent, into a blue-colored complex, and these color changes occurs in an alkaline solution in the presence of phenolic compounds. However, you must be aware of its limitation. The FC reagent is not perfectly specific. It detects all phenolic groups found in your extracts, including the bonds, those that bound to extractable proteins. So the major disadvantage of this assay is the interference from other reducing substances. Because of this, it is sometimes proposed as a measure of total reducing capacity of a sample rather than strictly used just polyphenols. So to perform the TPC determination, you prepare your FC reagent, a sodium carbonate solution to create the alkaline environment, and a gallic acid standard solution. So the gallic acid is used as the universal reference compound for this assay. When analyzing, the sample is measured against a reagent blank, and the reagent blank itself is measured against a water blank. We need the absorbance of the blue complex of 365 nanometers. Again, be highly cautious of your sample matrix. High level of fructose, sulfate, and ascorbic acid can interfere with this assay and give you artificially high readings. Finally, how do we express our assay's results? Because we use gallic acid as our standard, the results are expressed as total phenolics gallic acid equivalents, or GAE. So if you are analyzing a simple juice, the formula is straightforward. You take R, which is the reading from your standard curve in the milligrams per millimeter, and multiply it with the DF, the dilution factor. If you're determining the total phenolics in a solid plant extract, the formula is more involved. You calculate it as the R times TF times, okay? So times TV, the total volume of the extract made. You then divide the product by the sample volume used for the assay or SV, multiplied by the weight of the sample in gram, multiplied by 10,000 to get a percentage. And that wraps up our lecture today on the determination of vitamins and antioxidant. So we have covered titrations, lipid extraction, enzymatic digestion, and spectrophotometric assays. Thank you all for your time and attention.